Hi Heights High School, this is Louisa Revolt, and here is a few minutes of a talk that's sort of an overview of a variety of things that you guys have asked me about in the past. So astronomers use many different kinds of light to study things in space, and we learn very different things about objects when we look at them in many different wavelengths. So here I have the same galaxy in many different wavelengths. If you're using X-rays, you might use a satellite called Chandra and get an image that looks like this. If you're using ultraviolet, you might use a satellite called Galax and get an image like this. In the visible, you could be observing from the ground, but this image is from a spacecraft you may have heard of called Hubble Space Telescope. In the near infrared, you might use an all-sky survey from the ground called TUMAS, so you might use Spitzer and get an image like this. In the far infrared, you might use Spitzer or Herschel. It turns out both of those spacecraft have run out of cryogen, so they're no longer operating at the long wavelengths. But when Herschel was flying, you get an image like this. So we have wildly different wavelengths here. We're looking at things of wildly different temperatures, and we're seeing very different things. So in the X-rays, the wavelengths of light are maybe 2 nanometers. A nanometer is a billionth of a meter. We're looking at things that are maybe 1,000,000 Kelvin. And we're looking at things like black hole accretion disks. Ultraviolet wavelengths are about 200 nanometers. Temperatures of the things we're looking at are maybe 15,000 Kelvin. And we're looking at hot stars, which usually tend to be the young stars. In the optical, the wavelengths are about 500 nanometers or half a micron. Temperatures of things that we're looking at are maybe 6,000 Kelvin, and those are run-of-the-mill stars like our sun, but at all ages. In the near infrared, we're looking at wavelengths that are 1,600 nanometers, or about 1.6 microns. Things that are about 2,000 Kelvin, those tend to be very cool stars, which are usually the old stars. In the far infrared, the wavelengths are 100,000 nanometers, or 100 microns. We're looking at things that are maybe 30 Kelvin. We're looking at cool dust that's heated by the hot stars. I work for the Infrared Processing and Analysis Center, IPAC, here at Caltech, and we focus on infrared astronomy. We have a very different view of the electromagnetic spectrum because we do focus so much on infrared astronomy. So here I have the same little dog. On the left, there's a picture in visible light and optical. And on the right, it's an infrared light. There's two really important things to notice. One is that this is a remapped color image. I have taken the wavelengths of infrared light and I have translated them into optical light because you can see optical light, but you can't see infrared. If I hadn't done that, if I'd just given you an infrared picture, it would be that, because your eyes can't see infrared, and that would be pretty boring. The other important thing is that the way that I've translated the infrared wavelengths to light that you can see corresponds to a temperature scale. So the things that are black or blue or purple are cold, and the things that are white or yellow or orange are warm. So you can see he's got a water bowl here, which is nice and cool. He's a fluffy little dog, so you can sort of see the halo of fur around his head. His ears are warm, his face is warm, but because he's a healthy little dog, his nose is cold. So now you know that hot things glow in the infrared. Here I have a bathroom faucet that's running. There's pictures of it in the infrared. Which one of these has the cold water running and which one has the hot water running? The bottom one is the hot water. You can see that it's heating up the basin. The base of the faucet is warm. You can see that that cold water tap still has cold temperatures around the base of it. When the cold water is running, you can still see the base of the hot water temperature. The hot water spigot is still warm. So infrared can reveal things that are totally hidden in visible light. What do you think this is going to look like? I can tell you the hairdryer is on. So you can see the heating elements in the hairdryer, and you can see turbulence in the air that's coming out. Infrared can see through some things that are totally opaque to visible light. So here I have just a regular green garden garbage bag, and you can see straight through it in the infrared. Even though you can't see through it in the optical, you can see straight through it in the infrared. Turns out you personally are really glad for this property of infrared light, because if you are stuck unconscious in a burning building, that is how infrared light is how the firemen will find you. So optical light has a really hard time getting through smoke. But here in the infrared, you can clearly see the fireman standing on the steps. You can see his rebreathing apparatus is helping to keep him cool, and you can see that he's pretty hot under all of his gear. But he's got the infrared camera, so he's going to be able to find people who are injured or unconscious in a burning building. Some things, though, that are transparent in visible light are totally opaque in the infrared. Here's a set of French doors that are in my living room, and I've got one door open and one door closed. When I look in the optical, you can see easily through it, but in the infrared, you can't see through the glass as easily. You can see that I'm back there, but you can't see through the glass. And this, incidentally, is why when you park your car in the sun in August, when you get in the car, you can't touch your steering wheel, because what happens is the optical light comes through the windows of your car, heats up the inside of your car, and the infrared can't get out. So it just keeps heating up and heating up and heating up. So the next time that you are unable to touch the steering wheel of your car, remember the property of infrared, that infrared doesn't go through glass. So up until this point, you've been looking at things that you might encounter on an everyday basis. Now we're going to sort of leave that world a little bit. Here I have a dewar full of liquid nitrogen. A dewar is just a fancy name for basically a thermos bottle. Here I've got liquid nitrogen in the dewar, and I haven't put any frozen peas or anything else in the liquid nitrogen yet. So the infrared camera just looks at that, and that liquid nitrogen is 77 Kelvin, so it's actually much colder than the camera can see, so the camera just gives up and colors it all black. But if I put some frozen peas in the liquid nitrogen, they glow in the infrared. And that's kind of what's going on in space. Even though the peas are very, very cold, they are warm compared to the background, and so they show up in the infrared. So that's kind of how it works in space too. The things that we're looking at in space are often very cold, but they're warm compared to the background, so they glow in the infrared. Here's a picture of the familiar constellation Orion in the optical, and the same region of sky in the infrared. How much you miss if you stick with just the optical. So why do you need to go to space to do infrared astronomy? Well, here I have sort of a cartoon graphic of atmospheric transmission as a function of wavelength. And the main reason you have to go to space to do infrared astronomy is that the atmosphere absorbs infrared light. So if you're a gamma ray astronomer or an X-ray astronomer or an ultraviolet astronomer, you have no choice. You have to go to space because the atmosphere absorbs all of those wavelengths too. Optical light, of course, makes it down to the ground. There's windows in which the light make it down to the ground here as a result of the constituents of our atmosphere. Oxygen, carbon dioxide, water. It blocks a lot of the wavelengths, but if you pick your wavelength exactly right and you go to a very high, very dry site like Mauna Kea in Hawaii, you can observe in some wavelengths of infrared. But in order to do the mid or the far infrared, you don't have a choice. You have to go to space. And the radio, of course, the radio makes it all the way down to the ground, and you can observe in the radio from the ground. So that's the main reason why you have to go to space to do infrared astronomy, is because the atmosphere absorbs infrared light. The other reason is that space itself is cold. If you're going to observe tiny bits of heat from the outer reaches of the galaxy or the universe, you have to make sure that your telescope is cold. And if you are trying to observe in the infrared from the ground, it's really hard because your telescope is the same temperature as the air around it. And that's warm compared to the things that you see in space. And so you have to plan your observing differently when you're observing from the ground in the infrared versus from space in the infrared. Because the best analogy that I've heard is observing in the infrared from the ground with a warm telescope is kind of like observing in the optical from the ground with a telescope made out of those long fluorescent light tubes, because your telescope itself glows in the infrared. So in order to really observe in the infrared, it's a lot better to go to space, because then you avoid the warmth of the atmosphere. So why do astronomers need to study in so many different wavelengths? Well, we're studying things we can never ever visit. We can never ever put a star in a lab, watch it form, and watch it die. The timescales, the sizes, the distances are just not amenable to that. So we have to take advantage of all the light of any different wavelengths coming to us, and we have to decipher what it's telling us by combining the information across many different wavelengths. Because the infrared is really good at seeing through dust, if you study things in dusty places like young stars, this is a really good thing, and you want to do a lot of work in the infrared. So that's in fact what I do. I study baby stars. So this is a relatively nondescript region called IC 1396. It's sometimes called the Running Man. You can kind of see that there's a running man there. This particular object is in Cepheus, which is 3,000 light years away. This image is about the size of the full moon. The whole complex is about 10 full moons across. And this is an optical image. When I hit the button, it's going to fade into infrared. Let me do that again. So as I repeat this, you can look at the regions that are very, very dark in the optical, like here and there. And when we go to the infrared, it's not so dark anymore. It becomes pretty easy to see through it. So physically what's going on here is that we have very bright stars over to the left, and they're putting out enough ultraviolet light that it's kind of, you can sort of see that it's pushing around the gas and dust and evaporating off the front there, the front of the cloud. And so when the ultraviolet radiation is pushing around the gas and dust, it prompts star formation. So you can see this hole here is probably a star or a group of stars that was prompted to form by the bright stars pushing around the gas and dust, but then they're blowing their own hole in the gas and dust as they ignite hydrogen. So you can also see, watch these 4 stars. Here I can only see really one, and it's really bright. There's maybe one there. When I go to the infrared, there's 4 of them that are all about the same brightness. And so you can tell that by the fact that we can see these in the infrared, but we can't really see them in the optical, that they're pretty embedded, and so they're probably pretty young. There are some guys down here too that, are basically invisible in the optical that show themselves when you go to the infrared. So here's a cartoon that shows the formation of a low mass star. We have a big dark cloud with a dense core in it, and we're going to zoom in on one of these cores. So the length scale here is huge, and AU, remember, is the distance between the Earth and the Sun. So the distance scale here is like 200,000 astronomical units, or AUs. We're going to zoom in on just one of those cores. One of those cores has length scale of 10 or 20,000 AU, and we're going to start the clock. Things are going to start to collapse because gravity makes the rich get richer, right? So if something is a slightly more dense than the surroundings, things are going to fall in towards it, and it's going to get more mass than the surroundings, which is going to cause more stuff to fall in. You get a runaway effect. And eventually, you get stuff that starts to fall in at a greater and greater rate. And because of something called conservation of angular momentum, things don't just fall straight in. They basically fall into a disk, a CD, a record of matter before it falls into the central star. So you have this cocoon of matter in which things are kind of starting to fall in radially, but pretty quickly, in order to conserve angular momentum, it falls onto a disk. And then from the disk spirals into the star. For reasons nobody understands very well, a fraction of that matter that's accreting turns around and gets ejected at the poles of the star, creating big jets. Look at the length scale here, 500 AU. It's a lot smaller than 10,000 AU. And look at the ages. This is very, very young stars, 10,000 to 100,000 years. That's old by human standards, but very, very young by stellar standards. Eventually, that stuff, that envelope, either falls onto the disk or gets blown away by the jets. So you have just a big, thick disk, and sometimes, if the accretion rate is still high enough, big jets coming off of it. Look, it's gotten smaller because gravity's winning. Gravity's pushing in and pushing in. 100 AU and 100,000 to 3 million years. Eventually, that accretion disk thins out, and the jets turn off, and you end up forming protoplanets in the disk around the star. So it's about 100 AU, again, not a huge change in size, but now we're talking 3 million to 50 million years, and you get planets that form in that dust disk, and eventually they sweep up all the matter, and eventually you have a genuine, bona fide, mortgage-paying, hydrogen-burning adult star here. Length scale about 50 AU, time scale more than 50 million years. So these are the young adults, these are the teenagers, and these are the real babies. So I've got some movies here that demonstrate sort of that cartoon sequence. We have this big, thick disk and little bits of outflows coming out. We're going to zoom in first on the stuff in the disk. You can see that these granules are distinctly green when we zoom in a second. They turn out to be olivine, like green sand beaches in Hawaii, and they're covered in ices. So this is, all of these constituents are known to be in protoplanetary disks. The olivine and the ices, lots of ices, water ice, carbon dioxide ice, nitrogen ice, all of that is known to be in protoplanetary disks. This, of course, is just an artist concept, as are the other movies I'm going to show you. This movie starts out the same way, but now we're going to zoom in on the central object. So we're going to watch a planet form. Okay, it's starting to sweep up matter and create a gap, a hole in the disk, but you don't really see the planet till it sweeps up enough matter. There's the planet right there. So it's created a gap in the disk by sweeping up the matter and forming a planet. When you have this happening at many different distances, you end up with a whole bunch of gaps and rings in the disk as a result of the planets forming in the disk and sweeping up the dust. Where else have you seen this same kind of physics happening? You probably guessed Saturn. Saturn exactly has the same physics. It's exactly the same physics, just with a different central mass. You've got that disk around Saturn, much like a disk around a protoplanetary system, or a disk that is the protoplanetary system. Saturn's rings are probably formed by collisions. In other words, they're not left over from Saturn's formation. They are a result of moonlets and asteroids hitting each other when they're in orbit around Saturn. But it's the same kind of physics. You have all of these gaps and arcs and rings in the disk around Saturn, much like you have gaps and arcs and rings around protoplanetary protoplanetary systems around young stars. Now, it used to be that was the best example I could show you. This is relatively new data of a real star. This is not an artist's conception like the other stuff. This is a real image from Cassini. This is real data from a radio telescope called ALMA, and it is of a star called HL Tau. And this is the first time that people have been able to see quite so clearly the gaps in the disk around another star. This thing is relatively close, only 140 parsecs away. There's 3.26 light years in a parsec, so about 3 times 140 in light years, and you've got lots and lots of gaps in the dust ring, and that's really exciting because it may mean that we're seeing, doesn't guarantee, but it may mean that we're seeing planets form in this disk around this star. So now we're back to the artist's conceptions. When you have protoplanets forming in the disk, it's kind of crowded sometimes, and occasionally they hit each other, and they create a fantastic amount of secondary dust. This is not primordial dust, this is second generation dust. But that dust is still going to interact with the protoplanets and the disk of protoplanets around the young star. So you get lots of collisions, and you get dust rings and arcs that are relatively temporary, and eventually will get swept back up into planets. The reason I keep talking about dust is, of course, the infrared is sensitive to the dust, and so the dust in these young star systems is really important when you're observing in the infrared. So another artist conception, we're going to zoom out to the outer edges of this star system here, and there's a leftover ring of dust. What is this leftover ring of dust called when it's in our solar system? Remember that we passed Jupiter on the way out in this movie. Let's play it again. There's Jupiter. We're going to keep moving out. So what is the leftover debris in our solar system? It's the Kuiper Belt. So what is the difference between astronomy and astrology? Astrology is pseudoscience. It's not real science. It's the belief that the positioning of stars and planets affect events here on Earth. But that's not real. Astronomy is real science because astronomers are basing their studies on data, observations, and the physical laws of nature. So what is real science? So real science is very, very different than it may have been presented to you in classes or in textbooks. Science as presented in textbooks is usually science history, and it may seem like a never-ending series of right answers. But real science is nothing like that. Real science has a lot of dead ends and blind alleys and false starts because we're trying to figure out what the right answer is, and we don't know. There's no answer in the back of the book. So science problems as presented in textbooks or on quizzes have really well-defined problems. They have very specific methods you're supposed to use to solve them and very specific right answers. So you can get an answer of 1.2 and be wrong when 1.3 is right. But real science is very different. Real science is not exactly made up as you go along, but it may seem that way when you're starting out. And in reality, different people approach the same problem in different ways. And many answers can be right. You can have both 1.2 and 1.3 both be right, depending on the size of your error bars. This is not the same thing as there's no right answer. It is, what this means is there's no answer in the back of the book. There is a right answer. We just don't know what it is as we're struggling to figure it out. Really, in real science, the only way you know it's the right answer is if you understand each and every step you did to get there, and you believe that each and every step you did is the right thing to do. So just to emphasize, it's not the same thing as there's no right answer. There is a right answer, but there is no answer in the back of the book. Wrong answers get published because they believed everything they did to get there was right. So in labs you might have done to this point, you or your teacher or someone knows what the answer is going to be before you even start. You or somebody knows exactly what to do to get that answer. There's probably a list of instructions that you get that's a cookbook that tells you exactly what to do for your lab. Everyone in your class, and the class the previous year, and the year before that, and the year before that, everyone's supposed to do exactly the same series of steps. And probably you went through each step just once. You may or may not have understood what the purpose was of each and every step. And the report that you write up in the end has a very firm structure as a title, purpose, materials, procedure, conclusion. Or it may be that the entirety of your research means just going to the library or working on the web and summarizing what humankind already knows about a given topic and writing a term paper. But real scientific research doesn't look anything like that at all. Real research looks more like this. You have to first think of a question. It can be an entirely new question or leveraging off another project. Then you have to write a proposal to get money to pay your salary or telescope time or supercomputer access or whatever other resources you need to answer the question. Because you are literally wandering around on the forefront of human knowledge, you need to really understand each step that you're doing and believe that each step is the right thing to do. And more often than not, it's wrong, and you have to go back and redo it or try a different approach or completely restart it in a different direction. Sometimes, depending on your question, you have software tools or other tools or a way of thinking about it from another investigation that you can use in your new investigation. Sometimes that previous tool or approach works, and sometimes it doesn't. Sometimes you have to make major modifications or do something entirely different that works for your question. You have to spend an awful lot of time making sure that your analysis is not introducing artifacts or accepting instrumentational signatures as real. You have to make sure that the data are truly representative of what's going on, and I don't think I've ever reduced data just once. So what do I mean by artifacts? Here's an example. There's a picture of a high school football game at night. You know, based on your experiences, that those big bright lights are not really giant puffy balls with giant purple wings and streaks coming off of them reaching all the way to the ground. You know that. You know that from your experience. Those are artifacts. That is just how the camera and the detector in the camera is responding to these very bright lights. Same things happen in astronomical data. You can't take a picture and assert, yeah, there's these giant purple wings coming off these lights, because those giant purple wings aren't really there. It's just a result of how the camera is responding. And so that's what I mean by artifacts. You have to make sure that what you're looking at is really what's going on and not something that's caused by your camera or your instrument. Then an integral part of the research process is to talk about what you've done with colleagues. You have to say, hey, I've done this and this and this. I got stuck here. Do you have an idea of how I can get past it? Or do you agree with what I did in this part of the process? And in practice, you have to do it again and again and again and again and again and again and again if you need to. Or sometimes you just have to give up. You say, okay, this is not useful. This is not going to work. I have to try something else entirely or do a completely different project. If you do think it's okay and you understand everything that you've done and everyone that you've talked to says, yeah, I think you've done everything right. That's a really good result. Then you write it up very carefully and you submit it to a journal. What those journal editors do then is find another scientist in your field And they send that paper to these other scientists. And the other scientists write up a response. And those responses are usually anonymous. In other words, I don't know who's reviewing my paper. But they say, yes, I agree with this and this and this. It looks good. Go ahead and publish it. Or I completely disagree with what you did here in step 3. You need to fix it. And once you get past that peer review process, then the paper can be published. And you can begin again. You can come up with a new question. In reality, scientists are usually working on many different projects at once, in addition to doing whatever it is that pays the bills, whether that's teaching undergraduates or supporting spacecraft and archives like I do. So what are the differences between scientists and engineers? Science versus engineering. Engineers build things. Scientists learn about nature. In reality, there's a continuum of individuals. There are scientists that do lots of engineering and engineers that do lots of science. But pretty much there's 2 populations. There's 2 different cultures. I'll let you decide which one of those cultures between engineers and scientists like having meetings at 8 a.m. But, there's a division there. NASA has an awful lot of both engineers and scientists, but they have more engineers because they build a lot of things. Really good missions or telescopes or facilities of any sort come from engineers and scientists working closely together. They have to work really closely. They have to be involved. Both engineers and scientists need to be involved heavily in the project. So are scientists and engineers creative people? Yes, scientists and engineers are very creative people. So here's a real life example. We want to know whether or not life has ever existed on Mars, or could it have existed on Mars. So how are we going to find out? So the scientists go away and think, and they come back and they say, okay, life as we know it needs water. So we need to look for water now or ever in the past on Mars. So the best way we can think of to do that is to send a rolling robot geologist to Mars that can drive over all the rough terrain that you find on Mars. And it's going to need tools that enable it to be basically a robotic geologist. It needs to be able to drill into rock, vaporize bits of rock, and read the chemical signatures of that rock. And while it's at it, take a lot of pictures. That way, we will learn things that help us understand what Mars used to be like and whether or not it was ever wet. And the engineers are like, really? You want to vaporize rock? Okay, in order to do that, we're going to need a nuclear-powered thing, and with all the other requirements you've given us, it's going to have to be the size of a small car. We're going to need to figure out how to get it safely to Mars. It needs to fit inside this rocket, and it needs to unfold on its own when it gets there. And the best way we can think of to get it safely to Mars without damage to the spacecraft or with an impact on the science that you want to do is to have it lowered from a sky crane gently onto the surface. It needs to be able to drive itself autonomously within reason, because Mars is so far away. It's not like someone sitting with a joystick at JPL. It has to be able to drive itself because we don't have real-time communications to Mars. The only way you're going to solve problems like this is to be really creative. And creativity is absolutely critical to being able to solve problems like this. So specifically in the context of the rover, I just want to emphasize that engineers' primary work was in getting the rover safely to Mars. They were heavily involved in building it and testing it, but now that it's there and working, there's relatively few engineers left on the project. Most of those engineers have gone off to work on the next challenge. Many of them are working on a submarine that's going to go to Europa. So there's relatively little engineering now because the thing is built and tested and it's working. Scientists were involved from the beginning because they were able to tell the engineers, we need it to do this. And they were involved along the process, but they had relatively little to do until the spacecraft got to Mars. Now that the rover is there and working, the scientists are super busy. They're using the rover and they're learning about Mars. All right, things about careers. Most astronomers have PhDs, so that means college and graduate school. You will not pay for graduate school, most likely, which should take 6 to 8 years, but you probably will pay for college, which should take you about 4 years. It doesn't matter so much specifically where you go to college. You do need a solid base, a solid understanding. So you need to go to a place that works for you. If you want urban, rural, big, small, liberal arts, technical, you figure something that works for you, that you're going to be supported in a way that works for you, that you can be able to learn, because you need to learn a lot in college. You need to take as much physics, math, and computer science as you can possibly get your hands on to be an astronomer or a physicist. If you want to, depending on what kind of astronomer you want to be, you need to take chemistry and geology and biology as well, especially if you want to look for life. I would recommend that you major in physics because you need a really solid foundation for any other physical science. And honestly, if you decide after college to do something else, pretty much any HR department anywhere is going to be impressed when you tell them that you've majored in physics. You need to get into doing real research as soon as possible because research is absolutely nothing like classes. And there are plenty of people that excel in classes, but as soon as they experience real research, they're like, that's it, I'm out, because it's very, very different. Personally, I have my undergraduate degree in physics from the College of William and Mary in Virginia in 1992. My graduate degrees, both my master's and my PhD, are in astronomy and astrophysics from the University of Chicago. So these are the school skills for a good astronomer. You have to be tenacious. You can't let go. Once you get your teeth into a project, you can't let it go until you've solved it. You have to be creative, as we talked about. You have to have a lot of attention to detail. Astronomers basically fall all over the map in terms of personality metrics, but I suspect that we're all sort of OCD. We're all somewhere on that spectrum because you have to be really careful about details. You have to be willing to work really hard. You have to be self-motivated. You have to be able to communicate well, both in writing and in person. At least for astronomy, you need to know a lot of computer programming. I don't mean just using Word and Excel. I mean actually like Python, like programming the computer. You need to know lots of math and lots of physics. You need to know lots of astronomy. And depending on what you want to do in astronomy, you need to know lots of chemistry, geology, and even biology. Why did I do astronomy? I've always loved astronomy. Ever since I was really little, I was completely transfixed by anything having to do with NASA, especially Voyager images. I did fall off the wagon for a while in elementary school because I had bought into the idea that girls can't do math, which is complete garbage, obviously. What do I personally do? Well, a professor is hired to do research, but then also teach and serve the University of Community. I do research, but then instead of teaching and serving the community, I support a spacecraft and archives to serve the larger community of astronomers, not just the university community. I support something called the Infrared Science Archive, or IRSA, which is NASA's home for all sorts of NASA infrared data. I support a telescope called the Spitzer Space Telescope, which operates in the infrared. And it turns out I run a program that helps get teachers doing real research. It's called NITARP. I also do science, which means that I travel to conferences, I write proposals, I go on observing runs, I prepare observations, I reduce the data that I get, I write papers, and I give talks. So day to day, I work on my computer and attend meetings, both online and in person. Astronomers come basically in 4 flavors. You can be an observer, like I am. In other words, you go and observe things and try to understand what you're looking at. Theorists are going to make models of what might be going on in these astrophysical objects. Computer modelers are sort of hybrid observers and theorists. They make computer models and then they run many iterations of what happens if I make this mass bigger and that mass smaller, or what happens if I change the chemistry of the cloud. And then the last big category is instrument builders. They build the cameras for other, for astronomers to use. For other physical sciences, you can also have an experimentalist where they can put things in the lab, but we can't, as astronomers, put things in the lab very easily. So I'm an observer, which means that I get telescopes to give me data from all over the world and off of the world from spacecraft, and I try to understand how stars form based on the data that we take. No astronomer spends all of his or her time at a telescope, except for people who are actually paid to be the telescope operators. Most observers would be very, very lucky to get 5 nights of observing time per year, and we don't ever look through the telescope with our own eyes. We're always using cameras. It takes a surprising amount of time to turn data into papers. I mean, months to years. What the data that I'm working on right now was taken 2 years ago, and we still haven't managed to publish it because it's really difficult data to work with. I work here at Caltech in Pasadena, California, but there are conferences and observatories all over the world. Astronomers, out of all the physical scientists, I think travel the most. At least so I gather, we travel a lot. We're going to conferences, we're going to observing runs, we're going to team meetings and proposal reviews, and we go, visit our collaborators to work together closely on projects for, sometimes an extended period of time. Usually that means I'm going to places in North America and Europe, sometimes at South America because there's a lot of telescopes in Chile. Sometimes it also means South Africa and Japan and China, because all 3 of those countries, South Africa, Japan, and China, do lots of astronomy too. The Middle East and India are rising powers in this field. I have colleagues who travel almost every week or 2. I've had runs of things that are completely nuts. One year, I didn't actually spend 5 consecutive days in my office between March and August, and that was just I just died. It was really hard for me. But there are other people that it doesn't bother. They just, pack everything they need on their back like a snail, and they go. Before I had a kid, I traveled a lot more, and I made sure to take off extra time to go sightseeing wherever it was that I was going. But now that I've got a family, I'm more discerning about what conferences I go to, what committees I join, what responsibilities I take on, and what that means for my travel schedule, because it really impacts my family when I'm gone for an extended period of time. Sometimes for these meetings, I can participate online, but it's really hard. I think it's going to get easier in time as the online collaboration tools improve. But for a lot of things, you can't beat the serendipitous nature of, running into somebody while you're getting coffee or whatever. That's why people go to meetings, is to have those kinds of networking, that serendipitous kinds of conversations. So, job outlooks. So I have a question for you. What fraction do you think of the federal budget goes to NASA? Turns out NASA is less than 0.5%. So every tax dollar that you pay the government, less than half of a penny goes to NASA. And NASA does a lot more than just astrophysics. So astrophysics is a tiny fraction of that. The National Science Foundation supports astronomy too, but there too, it's not really that much money in terms of the fraction of the federal budget. It's really tiny. If you go look up the statistics at the Bureau of Labor, it lumps astronomers and physicists together, and they get 23,000. I figure there's probably about 8,000 astronomers in the U.S., but that number, different people get different numbers when they try to guess. What that means is it's a very tiny fraction of the federal budget, and there's not very many astronomers in the U.S. So small fluctuations in the federal budget can make an enormous difference in the number of astronomers that are employed. Giving you actual salary numbers is completely meaningless because, for example, the cost of housing where you live in Kansas is very different than Los Angeles. I think the most recent numbers I've seen is that the average rent in the city of Los Angeles is $2,500 or $3,000 a month. That's average, and that's got to be really much different than what it is in Kansas. There's also a huge range in salaries, ranging from a research professor at a top-flight research university like Caltech to telescope operators who live on remote mountaintops. There's a huge difference in salary. So, I make enough to have a house and a car. I have a husband and a kid and a cat. I make enough to live normally. Scientists tend to work a lot more than 40 hours per week. To me, when I was in high school, this sounded really horrible. But it turns out that if you love what you do, it doesn't feel so much like work. I also really, really enjoy working with smart, motivated people. When I was in high school, I hated group projects with a fiery passion because I was the only person in any of these group projects that actually cared enough to work. But when you're working with people, all of whom were that kid, all of us are smart and motivated, it's a lot of fun to work on big projects. It really is completely ridiculous that I get paid to have so much fun, and that's one of the things I love most about my job. It's also true that my job is very flexible. I usually leave a little bit early, twice a week, to take my kid to Taekwondo, or to make a parent-teacher conference, or whatever else I need to do. So other questions, the most common question I get is, the biggest, brightest, coolest, newest things that I observe. Well, I study star formation in our galaxy. So some of the clouds that I study are more than 100 light years across or even bigger. Some of the clouds I study are very, very close. So they may not be very big in physical units, but they look big to us because they're so close to us. So one of the clouds that I study is 260 square degrees. So for context, the moon is about a quarter square degree. So I'm studying a cloud that covers a huge fraction of the sky. But my paper that covers 260 square degrees didn't really cover that whole cloud. We had to omit parts of it because it was just too big. I study young stars that are going to eventually turn into stars like our sun, but because they're very young, they're nearly all bigger than the sun. So they usually are between 2 and 5 times larger than the sun. I have discovered more than several thousand young stars. The lowest mass, which means the coolest objects that I found, are late M or early L dwarfs, so like 3,000 Kelvin. Those are all the slides I have for you today. Hope you enjoyed it.